All right, so this is 7.3. Definitely some harder material in this unit when we're trying to graph these graphs. So today we're going to try to graph rational functions. All right, if you look at the beginning of these notes, a rational function is just a function, f of x, divided by another function, g of x. This whole first page of these notes, this is kind of like your cheat sheet over the next week or so to help you just kind of prepare and start to memorize how to graph all of these graphs in 7.3. There's a lot of different kinds. It's pretty rare that two of them look the same when you're trying to graph them, but the steps for graphing are all below. As you can see, it's ordered 1, 2, so on and so forth. And then inside of the steps, there's little things that we have to look at. And I'm going to go through those as we do a couple examples. But this page is kind of your cheat sheet, so you can come look back at it when you're trying these on your own. Step 5 here, this is kind of a catch-all. So it's all of the steps that are above it, but it's kind of condensed. So you can see all of the steps here. And then from that, you can go back and reference what other steps you would need to look at, or if you need more details. Step 6 is kind of just an add-on. You have to do step 6 at the end. Sometimes it's necessary to find some extra points that didn't get covered in the top section here. And again, you're going to see all of that as we go through these notes. So let's take a look at B first, because B is actually the easiest one to look at on this list. For any type of question like this, I'm going to always ask for all of these things. It's just a bunch of information about this graph. So the first thing we're looking for is the domain, discontinuity, and vertical asymptote. Those things are all related to each other, and they actually exist in the denominator of a fraction, because hopefully you remember the bottom of a fraction can never be equal to 0. That just is undefined in mathematics. We can't ever divide by 0. So what you need to do to find all of those first three items is we're going to set the bottom equal to 0, and we're going to solve for x. What this does effectively is it is going to show us what x value makes the denominator 0. So in this case, we get -1/2 would make this equation 0. And just like in our old graphs where we had like 2 over x plus 1, right, we said that there was a vertical asymptote at x equals -1. Well, we said that because, well, h in this case is -1. It shifts to the left 1. But what else is true about -1? If you plug -1 into this equation, it makes the bottom 0. So it actually comes from the same place as what we just did. So then we can say now that this x equals -1/2 is actually the vertical asymptote. So x equals -1/2 is a vertical asymptote. This type of discontinuity, when there's a vertical asymptote, we call it infinite discontinuity. And the location would be at x equals -1/2. And then the only restriction to the domain is that our x cannot be that value, -1/2, or we'd be dividing by 0. So we would say all real numbers, x cannot be -1/2. So just by setting the bottom equal to 0, we found all of that information out. So we come over here and we graph that, right? X equals -1/2 is a vertical line right at -1/2, and it's dashed because it's an asymptote. So it should look just like that. The next thing on this list, you can see it says HA/EB, which stands for horizontal asymptote or end behavior. In the past, you've known the end behavior as this thing called the horizontal asymptote, which is what we called it. But now I'm going to reference it more as the end behavior, because what it actually is showing us is what is happening at the ends of the graph. So when we're finding end behavior, I'm going to label it right here, end behavior / horizontal asymptote. What you have to do is you look at the highest degree x on both the top and the bottom. So in this case, it's just degree of 1. And we're going to stack them on top of each other and divide them. So this horizontal asymptote / end behavior is going to come from -5x divided by 2x. And then we're going to simplify this as much as possible. So x would cancel with x, and we'd be left with -5/2. So what does this tell us? This tells us that there's a horizontal asymptote / an end behavior that follows the line y equals negative 5 halves, and we can fill that information in down here. Y equals negative 5 halves. And then we can graph that. Negative 5 halves is negative 2.5. So it's going to be right here on our graph. And now these are starting to look like the graphs from 7.2, which does happen with some of these. Some of them look very similar to the graphs from 7.2. The next thing on our list is the y-intercept. Y-intercept always occurs when you plug in an x value of 0 into the original equation. So if we're trying to find the y-intercept, we're going to plug in 0 for x, so 1 minus 5 times 0 divided by 1 plus 2 times 0. That's going to give us 1 minus 0 over 1 plus 0, which is just 1 over 1, which is 1. So the point for the y-intercept, we plugged in 0 for x, we got out 1 for y, so 0, 1. And we can graph that point. So 0, up 1, puts us right here. The last bit of information that it's asking us about is this x-intercept, right? X-intercept is going to occur when the function, right? So we have 1 minus 5x over 1 plus 2x is equal to 0. The nice part about all of these rational functions is that as long as the numerator is equal to 0, the whole thing is equal to 0. Because if you have 0 divided by anything, say c, right, that would just be 0. So to find the x-intercept, we only really need to set the top equal to 0. Because if the top is equal to 0, the whole thing is 0. So now we can solve for x here. So 1 equals 5x divided by 5. We get 1/5 is equal to x. So our x-intercept is 1/5, and we found that when we set y equal to 0 in our equation. And then we can plot that point. Yes, a little bit harder to plot 1/5. It's going to put us right here. And now that we have 2 points, that is enough, because graphing these, they always hug the asymptote, go through any points that you found, and then they have to follow the end behavior or hug the horizontal asymptote in this case. Awesome. So that is only half of the graph, though, because we said the domain was all real numbers. So that means it should go to the left and the right. That tells us a couple things. First, I said that these are functions. So that means we cannot graph in this bottom quadrant, because if you tried to graph in the bottom quadrant, this graph would then fail the vertical line test, which means it would not be a function. So that means our only 2 options are there's either a section of graph here or a section of graph here that's going to the left forever. How do we find that? We're just going to plug in a point, right? You can plug in any x value as long as that x value is to the left of our vertical asymptote right there. So I like -1. -1's easy. It's just barely to the left of that vertical asymptote. So let's plug it in. We have 1 minus 5 times -1 divided by 1 plus 2 times -1 gives us a number. So that's 1 plus 5 over 1 minus 2. So that's 6 over -1, which gives us -6. So that's going to be the point -1, -6. And honestly, 1 point is good enough for me, because you should know we hug the end behavior horizontal asymptote, go through the point, and then hug the other asymptote, in this case the vertical asymptote. And so there's our graph, right? It's going to the right forever, going to the left forever, and it never crosses the vertical asymptote. And there it is. That's our first graph in 7.3. These graphs look all different, okay? So bear with me as we go through these. But the process for all of them is the same, which is kind of nice. So let's take a look at A now that we've done B. Makes A a little bit more doable. One thing that we did not have to do in B that shows up in A is actually factor the numerator or denominator. In this case, the denominator would factor. We'd have 2x squared on top, and in the bottom, this is a difference of squares. So we would have x plus 3, x minus 3 for our difference of squares. And You always want to factor these when possible. It just makes all of the rest of the steps usually a little bit easier. We will go back and forth between the original equation and the factored form, though, for different purposes. But factor it first, because what we want to do is we want to find the vertical asymptote. And again, to find the vertical asymptote, we set the denominator equal to 0. Well, when you have two things multiplied together and equal to 0, that means if A was 0 or B was 0, the whole thing would be 0. So that means we need to individually set each of those factors equal to 0. And now we can solve for x. I'll label this the vertical asymptote because that's what we're doing right now. So we have x equals -3 is one of the vertical asymptotes. And this graph actually has two vertical asymptotes, one at -3 and one at +3. So my vertical asymptotes, x equals -3, x equals +3. The discontinuity type is infinite discontinuity. And it's at x equals 3 and -3. And then the domain of this function is all real numbers. X cannot be 3 or -3. And that's all of that information. We can graph those now. We're going +3 is here. -3 on the other side. And then next we're going to find the horizontal asymptote slash end behavior. So we go horizontal asymptote slash end behavior. This is when we're going to use the original function again. We need the two leading terms, or the constants with the highest degrees. So this is going to be 2x squared divided by x squared. We're always going to reduce this as much as possible. X squared and x squared cancel. We're just left with 2. So that tells us that our horizontal asymptote slash end behavior is y equals 2. And then we can throw that on our graph as well. Perfect. Now that we have that, we can go y-intercept. Y-intercept, we plug in 0 for x. I like to go into the original equation when we do that. So y-intercept is going to be 2, 0 squared, divided by 0 squared minus 9. In this case, that would give us 0 divided by -9, which is just 0. So we plugged in 0, we got out 0. That gives us the origin, right? 0, 0. X-intercept then. The origin is a y-intercept. It's also an x-intercept, right? But to find the x-intercept exactly, we set the top, so 2x squared equal to 0. When we solve for x here, we can see again that x is just equal to 0, so our x-intercept is also 0, 0. So we filled out all of that information like it asks us to, but we only ended up with 1 point. So this question is a little bit more difficult because of that, right? In the middle of these graphs, remember, we call these new horizontal lines the end behaviors because it's telling us what happens at the ends of the graph. It should be hugging that line. But in the middle of this graph, you're allowed to go through end behavior. So the middle could look like this. The middle could look like this. The middle could look like a upside down parabola, sort of. The middle could look like a negative cubic function. It can look like a lot of different things. So we have to figure out what's going in the middle here. In order to tell if it's more cubic or more parabolic, all we need to do is we just need to check points to the left and right of the one that we're given, since it's right in the middle. So the easiest thing, I would probably plug in -1 and 1 into the original equation to find some points. So let's go ahead and do that. So we have 2 times 1 squared divided by 1 squared minus 9. So that's going to give us 2 over, did I do that right? Yeah, 2 over 1 squared, minus 9. So that's going to be -8. So that gives us -1/4. So when we plugged in 1, we got -1/4. That puts us right there. Let's also plug in -1 while we're here. So this is going to be 2, -1 squared over -1 squared minus 9 gives us 2 over 1 minus 9, 2 over negative 8, negative 1/4. So we went negative 1. It also gave us negative 1/4. So this middle section of this graph is going to look more parabolic. But remember, it's never going to cross those vertical asymptotes. Although we can cross end behaviors / horizontal asymptotes, we can still never cross vertical asymptotes with our graph. So that's what the middle section of this graph should look like. Fix this right side. Now it's about figuring out, well, where is the rest of this graph, right? We can't be in the top here. That wouldn't make a function. And then we can, the easiest thing, honestly, is probably to just plug in some points, right? So we need to go to the left of this vertical asymptote. So I like negative 4 right here. If we go to the right of that vertical asymptote, that would be positive 4. And let's just plug those in. So we're going to go 2 times negative 4 squared over negative 4 squared minus 9. So that's 2 times 16 over 16 minus 9, which gives us 32 over 7. Because I've done this question already, that's approximately 4.6. So it's going to be negative 4, 1, 2, 3, 4.6. Puts us right here. And then we're going to plug in 4, so that's 2 times 4 squared over 4 squared minus 9. So that's 2 times 16 over 16 minus 9. So that gives us 32 over 7 again, which again is 4.6. And those 2 points actually show us where these graphs are now, so they're going to be up here. Hug the vertical asymptote, come down and hug the end behavior. And then on the left side, hug the vertical asymptote, go through the point, hug the end behavior. And there's our graph, going to the left forever now. Has a middle section here, and it's also going to the right forever. All right. So again, these graphs usually do not look very similar. This looks very different than our first graph. One thing to note, as you get better at graphing these things, notice that the only x-intercept we found was the origin. In order for the graph to be on this bottom section, it would have to cross the x-axis again, which this equation, 2x squared in the top, only has a point right there at the origin. It is never allowed to cross the x-axis again. We found the only x-intercept. So that actually tells us, without even plotting either of these points, we can know that this graph section is going like this on the ends. All right, and again, this is really early to be talking about that, but hopefully it's something you pick up on as you practice more of these graphs. Okay, so we're going to do one more for the first day of notes. We're going to scroll down here to letter D, and we're going to try it out. Remember, when you start with these questions, you always factor what you can. So in this case, I'm going to factor the top. It would be x plus 2, x minus 1. In the bottom, we're going to get 2x plus 1 and x plus 2. Notice here that we have an x plus 2 in the top and an x plus 2 in the bottom. Well, hopefully you've guessed, these two things are going to cancel out. And this is a new special type of discontinuity called point discontinuity. And this point discontinuity exists at the x value of this factor that we just crossed out, that just canceled, right? So the x value, or the 0, is what I really mean to say. The 0 of that factor is x equals negative 2. So this is point discontinuity at x equals negative 2. Once you've crossed those two factors that cancel out, we're going to be left with the equation x minus 1 divided by 2x plus 1. And this is actually the equation we're going to use for the rest of this graph. So in order to find a more precise location of this point discontinuity, what we have to do is we have to plug negative 2 in for both of these x's. So a continuation of this point discontinuity, we're going to say negative 2 minus 1 divided by 2 times negative 2 plus 1. So it's going to be negative 3 over negative 4 plus 1, which is negative 3 over negative 3, which gives us 1. So when we're describing the discontinuity type, we would say point at, and that in this case we plugged in negative 2 and we got out a y value of 1. What does point discontinuity look like on a graph? Well, it's just a hole, so we're going to go to negative 2, and at 1 we're going to put a circle to denote that there is a hole in the graph at that point. So that's a new type of discontinuity. Those are the only two that we're going to see here: point discontinuity and then infinite discontinuity, which also exists here because the bottom cannot be equal to 0. So we have a vertical asymptote we need to find, and that's when we set the bottom, 2x plus 1, equal to 0, and solve for x. So then we have a vertical asymptote at x equals negative 1/2, which means there's infinite discontinuity at x equals negative 1/2. And now we can write the domain. The domain is all real numbers. X cannot be negative 2 because there's point discontinuity there. And it cannot be negative 1/2 because there's infinite discontinuity there. And we can draw in that infinite discontinuity at negative 1/2. Just like that. All right. So new type of discontinuity in this question. But let's continue, right? The next thing we need is horizontal asymptote / end behavior. So we look at our x's with the highest degree. So that's x over 2x. So our end behavior here is going to be x divided by 2x. The x's cancel and we're left with 1/2. So this is a horizontal line, y equals 1/2. And that's going to be right here. And we can actually graph this left side of the function right now because we have a horizontal asymptote / end behavior. And we're going through that hole in this graph. And then there's actually the left side of the graph. To find the right side of the graph, hopefully the y-intercept and x-intercept show it to us, right? So y-intercept, remember to find the y-intercept, x just has to be set equal to 0. So y-intercept, we're going to set x equal to 0 in our new equation, so 0 minus 1 divided by 2 times 0 plus 1. That's going to give us negative 1 over 0 plus 1, which is negative 1 over 1, which is just negative 1. So we plugged in 0, we got out negative 1 for our y-intercept. Can graph that one, 0, negative 1. And then for our x-intercept, we're going to set the top equal to 0. So 0 equals the top, x minus 1. And then we're just going to add that 1 to both sides to get x equals 1 for the x-intercept. So that's 1, 0. And the x and y-intercept do show us the other side of this graph, which is great. So we hug the vertical asymptote, go through the points, and we hug the horizontal asymptote. All right. So that's 3 of the more easier graphs from this section. Let me know what kind of questions you have when you come back to class. I would love to answer them. For the homework, I want you to only try out 3 of them. I want you to try out number 1, number 4, and number 6. Those are the 3 that are related to the examples that we did today. I hope you have a great day, and I hope to see you tomorrow.